molecular geometry. We try to explain a theory. It's called VSEPR theory. Okay, predicted the shapes of the molecules and polyatomic ion using the VSEPR theory. Explained the shapes of the molecules and accounted for the horizontal theory. So what we try to do here in this section is we try to explain how actually the shape of the molecule in this three-dimensional perspective. We want to know how actually the molecule look like. So in today's session, we will put the basis of these things, of this rule, with the help of two things. With Lowes dot structure diagram, first, this is the most important step. Second things, after that, with the valence shell electron pair repulsion theory, okay? So first, what actually the molecular geometry? A molecular geometry, guys, is the properties of the molecules depend on not only in the bonding of atoms, but also molecular geometry. What is the molecular geometry? The three-dimensional arrangement of the molecules of atoms. The polarity of each bond, along with the geometry of the molecule, determine the molecular polarity, or the uneven distribution of the molecule shape. We study the polarity, right? And we know that some atoms are actually in the covalent bondage is spending more time near to an atom because of high electronegativity, and this is forming a charge upon the high electronegativity with partial negative charge, with less electronegativity, partial positive charge, and we name this polarity, right? So the polarity with the molecular geometry affected the shape of the molecules. We try to explain how actually the shape of the molecule look like, okay? First, the molecular polarity strongly influences the forces of act between molecules in liquid and solid. A chemical formula by itself reveals little information about the molecular geometry. So we could from the chemical formula itself have some information about the molecular geometry. We will try to figure out how we could determine that. First is valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. As shown in right, diatomic molecules. So this is our basis, guys. We will talk about 2-atom molecules, 3-atom molecules, 4-atom molecules, and 5-atom molecules, and more. Okay? So we will put basis for each one to know what does the shape look like, how the angle look like, and how we could actually understand this according to the valence shell electron pair theory. First, we talk about the 2-atom molecules, like hydrogen chloride. Whatever, to predict the geometry of the more complicated molecules. So as you see that, what is the shape of these molecules here? Is there any possibility of any angles here? No, because it's 2 atoms, one here, one here. There is no possibility of 2 angles. So it's a linear molecules, right? And this angle here, we could consider it as 180. So the bonding atom. So we wanted to take this idea first to explain according to the valence shell electron pair repulsion theory. What actually the valence shell? The stress state that the repulsions between set of valence electron surrounding the atom causes the set of p oriented as far apart as possible. I want you to imagine this like 2 magnets with a similar poles. When we put it together, they will repel from each other, right? So if you try to force them to come closer to each other, what happens? They strongly repel, and they try to repel from each other. They are moving away from each other, right? In the valence shell electron pair repulsion theory, it is the same idea. But it told that the electron domain or the electron cloud, when they come closer to each other, these electrons have the similar charge, right? What kind of charge? Negative or positive? Negatively charged, like the electron is negatively charged. So the electron here and here in these atoms, when they come closer, there are similar charge. So according to the repulsions between them, they will move away from each other to give the atoms or the molecules specific shape and a specific angle. This is the main idea. This is the main idea of all the lesson. We will try to explain one of these atoms according to the type of the molecules and how many atoms are inside it. But we have a pre-steps to draw the Lowes data structure. Yes, Muhammad?
The repulsion indicates the shape of the limit?
Yeah, according to the theory, and we will see that. Okay.
The bonding needs to be 180 degrees.
Need to what?
Needs to be 180 degrees.
If it's linear, yes. But we will see how the bond angle actually determined, okay? According to the valence shell theory. So the valence shell electron repulsion theory states that the repulsions between the atom sets of valence level electrons surrounding an atom causes these sets of oriented as far apart as possible. Example, beryllium fluoride. How many atoms here, guys? How many atoms? 3. So this is 3 atom molecules. So let's explain the molecular geometry according to the type of atom from the beginning. Valence shell electron pair repulsion theory. Valence shell electron pair repulsion. Pair, electron pair. So first we said that if it's a simple molecule like 2 atoms molecule, like what, guys? Hydrogen H2, or oxygen O2, or nitrogen O2. Why I choose this example? Because it doesn't matter if it's a single, double, or triple bond. It will affect in certain cases, but it doesn't matter, because here for the hydrogen, if we draw the Lewis dot structure for it, H single bond and H, right? For the oxygen, oxygen double bond O, but we have here 2 lone pair, right? And here also 2 lone pair. For the nitrogen, triple bond with 2 lone pair here, right? To follow the octet rule. So what is the shape of the 2 atoms molecules, guys? Linear molecules. Do you understand why it's linear? Okay. So we understand this according to what valence shell electron pair repulsion. For example, here it's very clear here, guys, in the oxygen atom. We name this here the electron domain or the things. Do you see that? I have here 2 things, which is more comfy for the atoms to come closer like this to each other, or they move apart from each other, move away from each as far as possible to minimize the potential energy, right? As we recall it, when we study the chemical bond from the beginning of the chapter, we said that all the ones that try to form at the minimum potential energy. So this is a 2 atom molecules. Second things. 3 atoms molecule. A 3 atoms molecules. How actually it could shape according to the valence. The example that in your book is beryllium fluoride, right? BeF2. First step, what we do, guys? First step, what we do? Draw what? Lewis diagram or structure. So for the beryllium fluoride, what is the central atom here? Be is the central atom with 2 electrons, and we have the fluorine, right? Each one surrounded by how many? 7, right?
Yes.
So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And here is the shared bond here, right? As you see here, for you, if my hand is a central atoms, give me another pencil, guys, or a pen. And this is here the 2 things, or the 2 electron domain of the 2 fluorine atoms. So the atoms will come closer like this to each other. If we suppose that they come closer like this to each other, what happened to the fluorine atoms? We name this is 2 things, or 2 electron domain, or the electron cloud, according to the valence shell electron pair repulsion. If they are in that position, guys, what we will do? What we will do? Anas. If they are in that position, not like what I draw, if in the fluorine atom here and fluorine atom here and the polarium in the middle, they will repel, right? And the valence shell says that they will move apart as far as they could, right? Until they are in the position, they are actually linear. And this angle could be
180.
and the shape of the molecule, guys, is a linear molecule. This is a 3 atoms molecule. Do we have any lone pair upon the central atom here? Okay. Do we have any Do we have any, guys, do we have any lone pair up in the central atom? No. Remember, because we have cases here, 3 atom molecules with no lone pair up in the atoms, and we will know why. And if we have a lone pair up in the atom. Okay? Now, what is actually our second case? Yes?
B only has 4 electrons.
4 electrons? Yeah. It's not follow the octet rule. It's not follow the octet rule. There are 3 atoms molecules, guys. Carbon dioxide, CO2. How many atoms?
2.
Okay, let's draw. What is the first step I do it? Draw the lowest structures. What is the central atoms? Carbon, right? What is the shape of it? This is the lowest diagram of the carbon dioxide, right? Each one surrounded by how many? 8 electrons. Could you see that? We deal with the double bond as a single bond, and the shape of the molecules here, guys, is also linear. Does we have any lone pair up on the central atom here?
No.
Okay. Do you understand the steps, guys? We determine the number of atoms, we did draw the lowest structure, then we see the understanding of the valence shell electron pair repulsion, how the electron will repel from each other. Then we determine the shape and the angle 180 degree. Get it? So we talk about 2 atoms and 3 atom molecules have no lone pair up on the atoms. Okay, but if we have a 3 atoms molecules that have a lone pair up on the sulfur, yes, Yanis.
Why is the oxygen electron like this?
Because according to the repulsion, they will move apart from each other as we could to minimize the repulsion. Very good question, Yanis. Now, if we have a lone pair in the central atom like sulfur dioxide, atoms molecule, like SO2. This is one here, different from the previous example. It's have a lone pair up on its central atom. If we draw the sulfur, one of the oxygen forming a double bond, and the other, this is actually what I give you in the quiz, right? Okay. Here we have 2 lone pair. Here we have 2 lone pair here, guys. And here we have 6 lone pair. 3 lone pair. This is the shape of the structure of it. How many things here, guys, if they have 2 or 3? Things, like what I explained here. Here we have 2 things, 2 electron clouds, right? Here we have also 2 things. Here we have also 2 things, right? And it gives us a shape of a linear molecule. But here, what we have? What do you think? 3, right? Very good, Hamza. Why is it 3? Because I have here an electron domain here, and the lone pair guys here have considered as a thing or an electron domain. What we will do this electron pair here to know that the lone pair is occupying much space more than the shared one. How is that? Because the orbital in the shared one here, guys, it could not be stretched. This is the orbital here. It actually have a limited space to move in it, and could not be stretched or compressed like the lone pair here, because the lone pair here could move in like this or stretch be like this. This is what, according to the valence shell repulsion theory, we name that according to the valence shell electron pair repulsion. We know that it will actually have a force and make this bond here bent down, right? So the shape of it, imagine that I have here, the sulfur is my hand, okay? This is the bond of the oxygen atom, this is the double bond of the oxygen atom, and we're dealing with them as a single bond, right? And here is what? The lone pair, right? If I draw it like this, guys, if this is position here is actually to be the angle like 90 degree here, 90 degree here, and 180, is it comfy for the atoms? It's not. It's not comfy for the atom. So what is the actually, this is 2 lone pair here, applying that stress on the bond here, and make this angle go down a little bit. Go down a little bit, okay? And this is actually make the molecule look like this. The sulfur with the 2 lone pair here, and here is the oxygen atom, and here is the double bonded oxygen atom, and here is its own lone pair. And this shape here, we name it bent, because the lone pair is bent down the bond. And the angle here, guys, approximately what, guys? Equal how much? 120. But here this angle is 119, less than 120, because as I said, the lone pair occupy much space more than the shared pair. This shape here is bent. Okay? Yes?
When do I bend it?
If you have a lone pair here. So this is the shape of it. A 3-atom molecules with 1 lone pair. So what is this? Why this differ from this point? Because we don't have here any lone pair. This is the question that I have. We don't have any lone pair up on the central atom. Okay? Let's see that. What? Yeah, okay. So we talk about 3-atom molecules. Now we will talk about a 4-atom molecules. Boron. A 4-atom molecules, guys. Like BH3 in your book. This is how many atoms here? 4 atoms. What is the central atoms?
B.
B. This is one of the exception or not? Do you remember it?
Yes.
Okay. How many electron? 3. And how hydrogen I have? 3 hydrogen. Each one will share 1 electron. And this is the Lewis dot diagram. Are you following the steps what I do? First, I know the general formula. I write the Lewis diagram. Then I explain it according to the valence shell electron pair repulsion theory. Here we have the boron fluoride, right? Guys, here we have how many things we have here? Hamza, how many things?
3 shared.
3. 3 shared, so we have 3 things here. So it's more actually comfort for the atoms to be the angle here 90, and this is 180, or what support this atom to do? The atoms. The boron this bond will form. Do you see the angles, guys? 3 angles is equal, and this angle is equal 120. And we name this shape trigonal pyramidal, or trigonal planar. Why we name it this? Because as you see that, it's in the direction. Give me the pens again. Okay. Here is the hydrogen bond down. The hand represents the central atom. My hand represents the central atom, the boron. And here is what it's look like. Okay, Ali? Okay. There is how it's look like. Do you get it? 120 degree. And we name this shape trigonal planar. Okay? What we have here. As you said, if you look to the valence, we said that the chemical formula could be estimated how actually the shape of it look like. For example, if we talk, I told you that if we give AP2, this is a model of how many atoms molecules? 3 atoms, and we know that could be linear. And we represented the lone pair by another one is E. The AP4, a model of what? 5. AP3, a model of what, guys? And the shape, the part of going converted into equivalent to trigonal, giving 120 degree angle between the bond. AP4 are 5 atoms molecule shapes between the electron pairs of max minds of each AP, and one of the 4 carbon are tetrahedron. This is another shapes, but we will come back. So first here, BCl3, what he did, he counted the number to draw the Lewis dot structure. Then, what is the shape? What is the name of the shape? Trigonal planar. And the angle? The angle? 120. Perfect. Perfect, Tom. This shape here is trigonal planar. 120 degree, right? Is a model of how many atoms, guys?
4.
Very good. So we talk about 2 atom molecules, 3 atoms molecule, 3 atoms with lone pair, 4 atom molecule, and now we will talk about 4 atoms and to see if a lone pair will affect it or not. First, let's see here a 3 atom molecules with a lone pair. This is called what? ammonia. The ammonia here, guys, and the water. The lowest structure of the ammonia show that the central nitrogen atom have unshared electron pair. How many? How many lone pair? Lone pair. One lone pair upon the nitrogen. The valence shell postulate that the lone pair occupies a space around the nitrogen and just bonding pairs do. Taken into account, the unshared electron pair in H3 takes tetrahedral shape as an AP4. It's a AP3, but have one lone pair, and we, as we said, we consider a lone pair as a thing, as a bond, right? So we consider it as an AP4, and the shape of the molecule is referred to the position of the atoms only. The geometry of ammonia molecule is that a pyramid with triangle base. Let's explain this for atoms molecule. We will take the methane, CH4. It's a gas. So let's draw the lowest dot structure for it. What is the central atom?
C.
Yeah. 5 atoms molecules. Yeah. 5 atoms molecules. Sorry. 5 atom molecules. Okay. We know that the shape is tetrahedral. Well, we will know how it's tetrahedral right now. Now, the SCH4, first step, what we do? Lowest structure. What is the central atom? C. Surrounded by how many? 4 dots. And we have how many hydrogen atoms? 4 hydrogen atoms. What you see here, guys, could you estimate the bond angle here? 90 degrees, right? Right? It's a right angle, right? This is actually totally mean that you don't understand the main idea of this lesson. Because actually it's a flat. If you imagine like this, even me, I could imagine like 90 degrees. But it's a flat, if you understand that it's flat. But when we define the molecular geometry, guys, a 3-dimensional. Right? What mean of a 3-dimensional? Okay. Give me another pen, guys. The carbon is the central atom. The carbon is the central atom. Do you see that? As Muhammad said, it could be a right angle, right? But actually, what happened here, as you see, how many things here of electron domain that could repel according to the valence shell electron pair theory? 4 things, perfectly has. This 4 thing, what they do, they will move apart from each other and the repulsions will apply and make these atoms. I will show you how they repel, but let me just explain what happens. Okay, guys, do you see that? Okay, this is why you imagine it's 9 angle, but we said that it's 3-dimensional shape, right? So what happened in this bond is actually goes towards you like this, and this bond is back to me, towards me, and this angle is like this. Do you see the shape of it? It's a pyramid with a triangle base. And how we could represent this? We represented this by a specific diagrams, guys. The carbon here, we represent the bond that towards you is a solid bond one, like this. We have several ways to represent. So this is the first hydrogen. And the second one, that inside the board, we represented by a dashed. So this is the hydrogen here. And this is one here, is a Z, and this is one here. If you look to the shape here, the angle, do you see that? A pyramid with a triangle base. Get it? And the angle here, guys, is less 109.5. And this shape, we name it tetrahedral. Tetrahedral structures. Okay? What?
What's the 109.5?
This is the angle between the hydrogen and hydrogen bond. Less than 109. And this shape, 109.5. This shape called what, guys? 5 atoms molecules called what? Tetrahedral. Any 5 atoms molecule, tetrahedral. Now we wanted to explain the ammonia and the water. In the ammonia, we know that it's occupying much space than the lone pair occupying much space more than the shared pair as we consider. Now let's draw the ammonia to see how it's look like. The ammonia is NH3, right? It's 4 atom molecules, and we know that if it's 4 atom molecules, the shape of it is what? Trigonal, right? It's a trigonal shape. But let's see how it will look like. This is the nitrogen, the central atoms. Okay, here is the 3 hydrogen atoms. 1, 2, 3. How many things here, guys? Huh? 3 or 4? Huh? 4 or 3? What? Okay. How many things? How many electron domain? Sorry, NH3, ammonia, not ammonium. NH3. Very good. NH3. So how many things here? 4 things, 4 electron domain. Here, 2, 3, and 4. This is actually, well, 4 of the atoms to actually take a specific shape, and the atom also be looked like this. 1 of atom towards you, 1 in the back, 1 in that direction, 1 in that direction, and we name this trigonal pyramidal. Okay? It's like a central atom. This is the central atom, guys. 1 towards you, 1 in that direction, and 1 in that direction. And this is the central atom, and the lone pair is here. And we know that it's applying a force because it's stretched more or occupying more space than the shared one. Do you see how it's look like? Okay. And we name this shape trigonal pyramidal. Trigonal pyramidal. Could you explain the water molecules? But before that, let's make a summary for the thing that we said from the beginning of this class. Okay? We have 2 atoms molecules. What is the shape of it, guys? Linear. Right. Okay, if we have a 3 atoms molecules, it could be, according, I have to ask you questions. If there is a lone pair, if it's no, so it's what? Linear. If it's yes, like sulfur oxide that we take. If it's no, like what we take, PF2. The one 2 atoms molecule like H2 and 2. So this one is linear, but if it's yes, if it's have lone pair like sulfur dioxide, we name this bent. Okay, if it's 3 atoms, is it's 4 atom molecule. I have also to ask myself a question: if it's have lone pair or not, upon the central atom, of course. If it's no, so what is the shape of it? 4 atoms, trigonal planar. Trigonal planar. Like what example? What we get? PH3. Okay. If it's yes, it's a trigonal like NH3 that we just take it. It's a trigonal pyramidal. Okay, and if it's 5 atoms molecules, guys, it's only have one case. It's tetrahedral. This is the summary for all what we talk. There is another way, like here what we take, CH4. Here is like CH4. Do you understand the whole idea? So we talk about the pieces of the molecular geometry, guys, and the angle. I will leave this. I want just to get back to the slide to show that another way to summarize. Do you understand what is the shape this? Trigonal pyramidal. And here is also for the water, trigonal pyramidal. Guys, we have another way to represent this. The E here, as a general formula, A represented the number of the central atom, B represented the number of atom around it, E represented the number of what? Lone pair. The number of what? Lone pair. If there is another way, yes, in the table of your book, page what? 178, you could see that. This is the summary of what we take. If it's 2 atom molecules with no lone pair, so if it's linear, If it's two atom molecules with one lone pair, like what we take, the sulfur dioxide or secondum chloride, so it's bent. If it's a three atom with no lone pair, telugenar with one lone, four atom, it's tetrahedral. If it's three atoms with one lone pair, it's a trigonal pyramidal. If it's two atoms with two lone pair, it's bent like the water molecules, and we will explain it again. If it's five atoms, we name this trigonal bipyramids, two pyramids actually in a reverse, one up, one down. Do you see that? And the last thing, if it's a six atom molecule, it's what? Octahedral structures.